now we have Lea Bottini from University of Oxford, who will tell us about gap phases and phase transitions with categorical symmetries.
Thank you a lot for inviting me to speak. And this talk is based on works in collaboration with people in Oxford, Laksha, who's here, Daniel, who's another student, Sakura, my supervisor, and Apur, who's in Copenhagen. So the plan of the talk is that I will build on the story that Laksha told you about the categorical Landau paradigm. And I, in particular, will explain how we can characterize this using the SymTFT. And so, again, the idea is to extend the standard Landau paradigm where we take our symmetry S, not to be like a standard vanilla group-like symmetry, but a non-invertible symmetry, which is described by a fusion category. And so, in particular, the symmetry we consider will be only like finite symmetries that can be described in this fashion. And I will also be strictly working into the space-time dimensions. And these are some related works. And then I will discuss a lattice construction that involves what are called anion chains, and then I will conclude. So what is the SymTFT? The SymTFT is something that takes as input a two-dimensional quantum field theory that has symmetry S, described by some fusion category, and then it outputs a three-dimensional topological theory, Z of S, that also has topological lines called anions. And mathematically, this Z of S is what's called the Drinfeld center of the fusion category. So this 3D TQFT has two boundaries, a symmetry boundary on the left and a physical boundary on the right. And this left boundary is topological or gapped, and encodes all the symmetry properties of the theory. In particular, it has the property that the lines that live on this boundary reconstruct the fusion category S, which is the symmetry of my theory. So this encodes all the symmetry. And then the right boundary is in general non-topological, and it encodes all the dynamical information of the theory. And the idea of the SymTFT is that then my two-dimensional theory with the symmetry can be recovered as the interval compactification of this three-dimensional TQFT. So this is what is known as the sandwich construction. And it's very useful often in practical computation because it allows us to separate all the symmetry aspects of the theory and isolate them from the dynamics. And in particular, it allows us to infer symmetry properties of the theory that do not depend on the specific theory that we are considering, but that just depend on the symmetry I'm interested in studying. Okay, and this also gives a very convenient characterization of operators that are charged under the symmetry. So suppose that I want to construct an operator O in this theory charged under the symmetry, and this comes from a topological line in the SymTFT stretched between the two boundaries, like in this case. Because then when I take the sandwich compactification, I get a local operator O. And the fact that this operator is charged under the symmetry comes from the fact that also the symmetry lines S come from anions or topological lines in the SymTFT. And in particular, the line from which my operator comes from and the symmetry line have a non-trivial braiding in this 3D TQFT. And this braiding in the 3D TQFT becomes the charge of the operator in the 2D theory. So in this way, we can encode charged operators. This is where it's called an untwisted operator. But in principle, we can also have twisted sector operators, which are operators attached to symmetry lines. These are the type that Laksha described, for example, for Ising. And this happens when these topological lines completely ends on the physical boundary, but doesn't really terminate on the symmetry boundary, rather it remains a non-trivial topological line on the symmetry boundary. So in this fashion, we can also characterize operators that are charged under the symmetry. Okay, and one important piece of knowledge that we need to have is how we very concretely characterize topological or gapped boundaries of the SymTFT. And the idea is that these boundaries are characterized by the maximal set of lines that can terminate on them. So So this is something that is encoded in what are called Lagrangian algebras in these TQFTs. And Lagrangian algebras are nothing but a sum of topological lines, such that all the lines that appear here in this sum can end on the symmetry boundary. They become trivial. And one can think of like imposing, as we are imposing the Dirichlet boundary condition of them, so they are completely annihilated on this symmetry boundary. While the lines that do not appear in this Lagrangian algebra do not end on the symmetry boundary, they remain non-trivial, and they remain a non-trivial topological line here on the symmetry boundary. So this is like giving them Neumann boundary conditions. And these are the lines that actually become the symmetry generator on the symmetry boundary. So the slogan is that gap boundaries are specified by these Lagrangian algebras in the 3D TQFT. Okay? And so now, once we have that, we can develop a framework to classify all the possible gap phases into dimensions that are asymmetric. So all the 2D asymmetric TQFTs. And the idea is that we start with our input fusion category S, and our first step is to construct this 3D TQFT, which is the SymTFT. Then we need to classify all possible gap boundary conditions, and as I was saying, this amounts to classifying all these Lagrangian algebras in the 3D TQFTs. Now, we want to study not any TQFT, but a TQFT that is asymmetric, which means that I need to fix my symmetry boundary to be the one that I want that generates the symmetry S. So among all of these gap boundary conditions, there is going to be one, which I called LS, that is precisely like that, is such that on this boundary I realize the symmetry S. And now regarding the other boundary condition, the physical boundary condition, this is normally non-topological because it encodes all the dynamics of a QFT, so it would have nothing to do with Lagrangian algebras. But we're interested in studying TQFTs. So in this particular instance, also this boundary has to be topological, such that when I take this interval compactification, I actually get a TQFT. So to obtain a TQFT, also the physical boundary is specified by a Lagrangian algebra, which I call the L-phys. And now the idea is that if I fix LS, so I fix the symmetry boundary to be the one that gives me the symmetry that I want, and then I cycle through all the possible gap boundary conditions for the physical boundary, this is gonna span for me all the possible asymmetric TQFTs that I can obtain. And this is a particularly useful framework because it allows us to obtain a lot of information about this gap phase with asymmetry. For example, I can define generalized order parameters, like the standard Landau paradigm order parameters, but for non-invertible symmetries. And as I was saying, like the charged operators are characterized by lines that end on the physical boundaries. So these are going to be given precisely by the anyons that appear in this physical Lagrangian. So I can immediately characterize the order parameters. I also immediately know the number of vacua of this TQFT. These are the anyons that can completely end on both boundaries, so that when I take the sandwich, I actually get a local operator. Then I can also know the action of the symmetry on the vacua very explicitly. And this is a framework that can also be extended to incorporate this transition, which I don't think I will have the time to discuss. So let me go back to the example that Laksha mentioned. So the non-invertible symmetry RepS3. This is given by the representations of the permutation group of 3 elements. And I'm using, thankfully, the same notation as Laksha. So E is the non-invertible symmetry, and P is the Z2 subsymmetry here. And now, let's say I want to characterize all the possible gap phases with RepS3 symmetry. As I was saying, the first step is to construct the Drinfeld center. And we know to construct the SymTFT. It turns out that the lines or the anyons that live in this SymTFT are simply labeled by a conjugacy class of S3. And then you take an arbitrary element in this conjugacy class, you look at the centralizer, and they are labeled also by an irreducible representation of this centralizer. So in S3, I have the conjugacy class of the identity that, of course, has the fullest commutes with the full S3. So I get 3 lines labeled by a representation of S3. Then I have the A conjugacy class. A is one of the cyclic permutations. Is a Z3 centralizer, so I get 3 lines labeled by a Z3 representation, which I denote by omega. And then I have the B conjugacy class. B is one of the transposition in S3. This is a Z2 centralizer, and then I get 2 anions, B plus, B minus, where this is a Z2 representation. And it turns out that I have, like now that I have all the anions and I know what the SymTFT is, I can do the exercise of computing all the Lagrangian algebras. This is just amounts to solving a bunch of like algebraic conditions, and it turns out that there are 4 Lagrangian algebras. In particular, this one, L4, is the one that has the property that realizes rep S3 symmetry, so it's the one that I fix as my left symmetry boundary. And then, since I know that there are 4 Lagrangian algebras, from our framework, we know that there are 4 gapped phases. These are precisely the 4 gapped phases that Laksha mentioned. So notice that like in this now SymTFT picture that I'm doing in just 2 dimensions, I keep this boundary fixed, L4, to be the boundary that gives me rep S3. And then I can change all the physical boundary and using L1, then L2, L3, L4, and I get all the rep S3 symmetric phases in this way. Okay, now in the remaining time I will briefly mention lattice models. And now the idea is that we want to construct lattice models that provide concrete UV models that flow to these gapped and gapless phases that we discussed using the SymTFT. And to do that, it's very natural to use anion chains, because anion chains are something that are naturally defined with the action of a fusion category symmetry. So the data that defines the model will be an input fusion category C, that in general is something different from the symmetry I want. And then what is known as a C module category M. So if you don't know what a module category is, this is, it's not important, but the important thing is that M is something that has a left C action. So I can define this product C times M into M, which means that I can end lines coming from C on lines in M. And then some object in this, some element in this input fusion category. And then basically this is the state space of the lattice model. So it is spanned by diagrams of this form, where the horizontal edge is an element in the module category M, and then I can end on it elements in C using this product. So the state space of the model is spanned by these diagrams here. And then I can define a symmetry acting on this state space. And it turns out that the symmetry in this case is what is called C dual M. This is the dual symmetry with respect from C, and it's obtained via some generalized gauging procedure. And the symmetry acts in this way: you take a line, a symmetry line, and you fuse it on the state space of the model from below. This in general will change this labeling here, and this is the symmetry action. And then our claim is that we can also write down gapped Hamiltonians. So for every gapped phase we determine from the SymTFT, you can also write down an Hamiltonian, and the ground states of this Hamiltonian realize all the gapped phases we found in the continuum. And in particular, the Hamiltonian is given by these sort of H operators that you glue on top here, on top of the fusion tree. And to realize a gapped Hamiltonian, the claim is that you need to specify these legs here to be what it's known as an algebra object. And in particular, notice that the symmetry commutes with the Hamiltonian as the symmetry acts from below, while the Hamiltonian acts on the top of the fusion tree. So S is indeed a symmetry. And this is a consistent picture with what we found before, because it's a mathematical theorem that gap boundaries of the SymTFT are actually in one-to-one correspondence with these algebra object things. And we claim that both of these classify as symmetric TQFTs. So I don't think I have time to actually enter the details for FS3, but here it's just fleshing how, in principle, we can construct this onion chain for FS3. And then this is essentially, by translating this, is how we write the spin chain model that Laksha presented in his talk. So in some cases, it's very natural to translate between this onion chain construction, which is very general, and for any fusion category, to some more standard spin chain that look like the Ising model. And let me end with the conclusion slide. Thank you.
Thank you. Yeah, so when you're writing down these S-symmetric TQFTs,
Yeah.
so I guess I have two questions that are sort of related. So what is S allowed to be, and what is the TQFT? So for example, is the TQFT like Turaya-Vero, which sort of tells you like what S needs to be?
So I'm doing I strictly work in 2 dimensions in this talk. Then there is a paper by Laksha recently that extends this 2D to 3D, but it will only be in 2D. And then S is a fusion category, and just any fusion category with a finite number of simple objects.
Which maybe, do you have to specify braiding relations?
No, because I'm in 2 dimensions, so it's not like a MPC where you have braiding, etc. This is like 2 dimension, it's a vanilla fusion category. Essentially, you need to specify a set of line operators. Those are your symmetry generators, and I will consider fusion categories that have only a finite number of those. Then you specify the quantum dimension, the fusion, and the F symbols, namely the anomaly, and this is basically all the data that enters in this definition of S.
I see. So then you write, then you say if I take that S, I can write down like the Turaya-Vero construction for TQFTs for any fusion category.
This will be the SymTFT essentially.
Yes.
The Turaya-Vero based on S. Yes.
I see.
But the Turaya-Vero is the SymTFT. It's not the TQFT that describes the.
No, that's right. I want to ask about the SymTFT. So I was confused because somewhere you take a Drinfeld center, and the Drinfeld center is usually a thing I would think of in like Reshetikhin-Turayev TQFT instead of Turaya-Vero, and so I with gapped boundary it's the same. Okay, so that's why you take the Drinfeld center. Oh, great, thank you.
Hi, so I have a simple question actually. So you made the assumption that the fusion categories are finite. So is there a specific reason for that? So if you don't assume that, what specific difficulties would you have in your analysis?
So I don't know how to treat fusion category with an infinite number of simple objects. So it's my simple fusion category, and I don't know, maybe Laksha knows better what's the mathematical literature at that point. But definitely in this case, where you can construct the Drinfeld center and it has, so the SymTFT and it has a very well-known construction, the important thing is that this, like the crucial point for us is to be able to classify gap boundary conditions. And in this instance, it's a very algorithmic procedure to classify all the gap boundaries. So I know how to take the symmetry S and compute all of these Lagrangian algebras. I honestly don't know how this carries out in the case of fusion categories with an infinite number of simple objects.
Okay, thank you.
There are no other questions, so let's not really.
If I can, is the time?
Yeah, it's okay.
I can just, in the simple special case of like continuous one-form symmetry, let's say, do you expect this paradigm to reduce to the Landau paradigm of the geometry we could be?
Right, so another, here I'm working in 2 dimensions and I'm considering only zero-form symmetry. So having a one-form symmetry in 2 dimensions will actually mean that you have topological local operators. this causes like a decomposition into universes of the QFT, and it's something that we don't consider here.
Yeah, also
So we don't consider multi-fusion categories. In higher dimension, it's a work in progress because we didn't really extend this or developed it as much beyond 2D. So I guess it's a question for the future. I don't know if you discussed it.
We can discuss it. So, let's thank Lea.
Thanks.